All right, so we were talking about limiting reactant, and we talked about it before in the sense of just moles. And now, because we know how to do grams, we're going to go back to this with grams. So the overall process of limiting reactants basically states that the number of Oreos or products you can make depends on both how many reactants you have. So if you have enough wafers to make 1,000,000 Oreos, but you only have enough cream to make 10 Oreos, then you're only going to make 10 Oreos because the wafers aren't going to become Oreos unless they have cream. And so if you only have enough cream to make 10 Oreos, then that's the only number you'll make, provided you had enough wafers to make that many. So whichever one of these reactants is in the lower amount to make product is the one that is considered the limiting reactant. So we did this with just moles, and now what we're going to do is, so that's what this was. So if you have 27 wafers, you want to figure out how many Oreos those wafers make. And you know, 2 wafers make 1 Oreo. And therefore, that's about 13.5 Oreos that you can make. But with 27 grams of cream, and you know that there's 3 grams of cream per Oreo, and 1 Oreo, that means you can only make 9 Oreos. So even though you had enough wafers for 13.5 Oreos, you're only going to be able to make 9 Oreos, and that makes the cream the limiting reactant. It's the reactant that is keeping you from making more. It gets all used up, and the other reactant is still in excess, but it doesn't matter because it has nothing to get together with. So you are going to need your stoichiometry highway, which I've now put into blue and purple and red. You're going to come in with grams of one thing. In this case, we had wafers, and we have to use this sort of transfer station to go from wafers to product, from wafers to Oreos. And that's what the balanced equation is. The balanced equation is that area of what we're doing that can translate from one thing to another. So here we're going from wafers to Oreos, here we're going from creams to Oreos, and that's coming from this balanced equation. So you're going to need that balanced equation to go from moles of one thing to moles of another. Beyond that, you can go from grams of one to grams of the other, grams to moles using the periodic table like we did last unit, or last semester. So let's take a look at this. I really wish I could get this out of the way without turning it off. Let's see if I can do that. All right, so nitrogen and hydrogen react to form ammonia gas. If you start with 40 grams of hydrogen and 40 grams of nitrogen, what is the limiting reactant? Now, in the last time we were doing this, you sort of learned that mole ratios, and a lot of you started just seeing it. But now that we're using grams, that's a whole different ballgame because certain things weigh different. And if you have the same amount of gram-wise, then you have to figure out how many moles you have before you can start doing that visual thing that you've been doing up till now. So the question here is, what is the limiting reactant? So we start with our balanced equation that nitrogen and 3 hydrogen make ammonia. That's all good, and this is telling you that there's a 1-to-3 ratio of moles of nitrogen to hydrogen to make 2 ammonias. That's all great, but we have grams, not moles, and it turns out because nitrogen is starting with grams, we're going to have to, if you look at that highway again, go to the periodic table to get it to moles. And nitrogen weighs a fair amount. There's 2 nitrogen atoms in a molecule of nitrogen. Each one weighs 14, so that's a total of 28 grams in 1 mole of nitrogen. And now we can use the balanced equation to go to product. Here is the product side of things. So we're trying to get to that side of things. And in doing so, we know that there's 1 mole of nitrogen in the balanced equation, 1 mole of nitrogen for every 2 moles of product. And so now we've turned from nitrogen to ammonia, and we know that the 40, so 40 times 1 times 2 is 80. That's where the 80 came from. It's this times this times this. And the 28 came from 28 times 1 to get 28. Now we divide 80 by 28, and we get 2.86 moles of ammonia. So what we have here is how many moles of ammonia 40 grams of nitrogen can make. Now we need to go to the next one, the hydrogen, and see how many 40 grams of hydrogen that can make. So 40 grams of hydrogen, using the periodic table, we'll have 2 grams of hydrogen for every mole of hydrogen. So we're getting out of grams into moles. So then we can, and then we use the periodic table to do that. So then we can use the balanced equation to figure out how many moles of product we're going to get. So the next step uses the balanced equation. The 3 comes from here, this 3 in the balanced equation, and the 2 comes from here in the balanced equation. So it's a 3-to-2 ratio of hydrogen to ammonia. And we get 40 times 1 times 2 is 80 moles of ammonia, divided by 2 times 3 is 6. So it turns out hydrogen, because even though it's the same mass of hydrogen as nitrogen, because hydrogen weighs so much less, you can make a lot more ammonia than you could with the nitrogen. So it's a little harder to see because there's 2 things influencing this. One is the mass and one is the ratio of moles. And it's really difficult for you to see that just by looking at it. You're going to have to do some of these calculations to figure this out. So in summation, what we have here is, because you have 2 givens, 40 grams of hydrogen and 40 grams of nitrogen, right? 2 givens in the problem. That means you're going to have to set up 2 ladders, or whatever you want to call these. And then you figure out products. You're trying to go to product. And in the end, the one that makes the least amount of product, which in this case is nitrogen, is your limiting. So nitrogen turns out to be limiting because it makes the least amount of product. And this implies that we'd have all sorts of hydrogen left over, but it doesn't matter because we're out of nitrogen. All right, so that is how we're going to do limiting reactants one more time, this time going from grams to moles instead of just moles to moles like we did before. And then we met this guy with a percent yield. And if you recall, basically what this was to teach you is, you put money in a vending machine, you expect something out. And if you don't get something out, you're upset because your percent yield is what you get divided by what you expect. And so initially, this guy expected that he'd get 1 piece of candy and he got none. And that's why he was so angry and kicking the machine. It got to a point where some nice stranger gave him some money so he could try again. So his expect went to 2, and he was hopeful, and he got, initially, he got 1, and then the second one got stuck. So that was a 0. So this one was 0% yield. He went up to 50% yield when he got 1, but he was expecting 2. And then after some more kicking, he got 2 after he expected 2, and that was 100% yield. And the same is true with chemistry, that when we are doing chemicals reactions, we expect things to happen. And so what we receive should be in the ballpark of what we expect. And we calculate what we expect. So this comes from the equation. So doing stoichiometry, equation calculations, basically, right? Doing calculations. There we go. That's what the amount expected comes. The amount received can only be determined from a lab. You have to do a lab experiment and actually weigh something out. And we did a lab with this, with trying to figure out how much carbon dioxide we got by putting vinegar and baking soda together. So let's take a look here at a sample problem. And then again, hopefully this doesn't turn off when I move that. So you have 25 grams of barium chlorate and excess sodium nitrate and the reactant double displacement reaction. You get 12 grams of barium nitrate formed. So this is what you get in the lab. Oh no, go back. This is what you get in the lab. All right, what's the percent yield? So you got this 12.7 grams of barium nitrate. The question is, what should we have gotten? So the balanced equation in this case, oh gosh, what was I thinking? All right, the balanced equation in this case is barium chlorate, ClO3, 2, and sodium nitrate, NaNO3, becomes barium nitrate, BaNO3, 2, and sodium chlorate, NaClO3. And so that's a 2, and that's a 2. That's what you get. All right, so given is you started with 25 grams of this starting material, this barium chlorate, this stuff here. So 25.0 grams BaClO3, 2. And we need to figure out how much barium nitrate that should have done. So we're going to need to do so we're looking for barium nitrate, and that's going to be in grams. Because we know this is what we got. We got 12.7 grams of barium nitrate. We need to know how much we should have gotten. So we go to the periodic table and we determine what the mass of barium chlorate is. And if we do that, we're going to find that barium chlorate weighs 304.23. So there is 304.23 grams of barium chlorate per every, and that's whenever we do the the periodic table, that's in 1 mole of barium chlorate. All right, so that gets rid of grams, and now we got moles. So if you look at our little pathway, we've used the periodic table to get into moles of one substance. Now we can use the balanced equation to get from the substance we start with to the substance we're trying to get to, which is in this case is barium nitrate. And you can see there is a 1-to-1 relationship between barium chlorate and barium nitrate. So barium chlorate is 1 mole and 1 mole of barium nitrate. Barium nitrate is 1 mole. So it's a 1-to-1. And then the last thing we need to do, that was just a little much. The last thing we need to do is to figure out the mass of barium nitrate to go from moles of barium nitrate to grams. And that's 261.3. So 261.3 grams for every 1 mole of barium nitrate. 2. All right. So you multiply the tops, 25 times 1 times 1 times 261.3, divide by the bottoms, which is 304 times 1 times 1, and you get, hopefully, as I'm doing this on my calculator, I should be more prepared. That's that divided by 304.23 is 21.4 grams. So you should have gotten 21.4 grams according to our calculations. What you did get is 12.7 grams. So our percent yield is what we got, 12.7 divided by what we calculated what we expected, which is 21.4. And 12.7 divided by 21.4 is 59% yield. So that was our yield. We got 59% of what should have been in that reaction. And as you've learned in lab, that you could spill things, you can, in this case, maybe not precipitate it all out. Some may have stayed dissolved in water. You could have had some go under the filter paper and into the flask so that you didn't catch it as a solid. There's a lot of things that can happen that would lower your yield, but you should know how to calculate a yield. All right. That is that. So good work, kids. I think that's enough for everybody.